Hello everyone, we are from section 2 group 1. So today we are going to demonstrate how to design a Gaussian filter using high-level synthesis. So first of all, a Python code to convert the image into a .dat file. So here is the folder which I save the data. So yeah, there are 3 images inside the data. So we have these 3 images, we convert it into the .dat file. Okay, after we running the Python code just now, we have get all the data for all the 3 photos. So we next proceed with running with the Gaussian.py. So we set as the start file first. So from this Python code, you can see here is the Gaussian filter 121242 divided by 16. And we will load the Lena data, Lena 512, building, and also Pikachu into the Python code. And then we will perform the filtering progress, apply Gaussian filter data. So we will run the code right now. So after running the code, we can see we have the filtered data for building filtered, Pikachu filtered, and Lena 512 filtered. So this will be the filtered result to be compared with the C++ code later. So next we will import the source file, which is from the group assignment folder. We have already written the fir.hash, the header file, and our Gaussian filter. Then we have our test bench. For the filter source file, we will perform the same function as the Python code as previous shown, which is the Gaussian kernel is here over here. So we will calculate and filter the photo. And here is the test bench. So for the test bench, we will load the data from the previous folder, which is building Lena 512 and Pikachu. We will run C simulations, clean build, press OK. So after running the code, we can see that after comparing the output file and the golden output file, which is the filtered .dat, the output matches the golden output for buildings, Lena, and Pikachu. So it means that all our Python code and C++ perform the same function and the outputs are the same. After we done all the filtering, we compare the result, we get a good result. So we will proceed with the synthesis. So first of all, we will go project setting. So we go synthesis. So we need to specify the top function, which is Gauss-filter.cpp. So click OK. So we go solution, run C synthesis, and active solution. So we will start the synthesis. So the clock period will be set to 10. This will be Vivado IP for target. So press OK. So the synthesis progress start now. Here is the result of the synthesis summary. So we'll see from here. Yeah, here is actually the output result. From here, our target is 10 nanoseconds. So our estimated time for us to run the code is actually 7 nanoseconds. So from here, you can see the latency is around 1 million. Yeah, and then the iteration latency is 2123. And then the trip count is 510. And then we can go to see our Verilog codes from here. So yeah, this is our Verilog code, which is apply Gaussian filter. So here are the input, output, and also the parameters. Yeah. So next we will go for the run the C and RTL core simulations. So we set the Vivado and we have the pop. So okay. You can see from here. Yeah. This is the image. So after we have generated the Verilog code in the Vitis HLS. So we go for the Vivado. So we will first create a project. We will add our source file. We will design source. So we add our source. First of all, we will go back to the previous one, which is the Gaussian FIR in the Vitis. So we go to synthesis, Verilog code. So all the file here we select. Press OK. So next we're going to create the IP. So we need to filter one by one. So second one, create the IP. So after we done everything, we can start to open the elaborate design. So click OK. So here's our schematic diagram. So here's the project summary. Since we haven't run the synthesis and implementation, there's no result here. So here's our schematic design. So the next step, we are going to give the time constraint. So we're going for the report clock network. So we could just OK for the network. We go to the time constraint. Hit clock. So we just set it as default. The pre will be 10 nanoseconds and the for will be 5 nanoseconds. Click OK. So this timing constraint, we just click the add clock, hit apply. The clock is already run, so we will run the synthesis. Okay. Constraint. After the synthesis is successfully completed, so we will keep running the implementation. So the implementation is completed, so we can view the reports for more information. So here's the report. So we can go to the project summary. So from here, we can see this is the total power consumptions. So this is the percentage, which is we can see that 33% of the power is used for dynamic and 67 is static. And we have see the table here is the output of synthesis table. So for the timing constraint, the worst negative slack is 4.767 nanoseconds. With total number of endpoints is 13659.